All right, so yesterday we finished up talking about the simple counting principles. Number 1 said determine the ways in which a computer can randomly generate a pair of distinct integers from 1 to 15 whose sum is 20. So we're just trying to figure those out, right? So if I had 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and I wanted to randomly generate a pair of distinguished integers. That means the two are coming at the same time. What does distinct integers tell you? You can't repeat it, right? So I can't use 10 and 10. That would not be distinct, right? So distinct integers from 20 would be what? What's one way I can make 20 from these? 5 and 15. What else? 11 and 9. What else? 6 and 14. What else? 7 and 13. What else? 8 and 12. And then 9, 11 would be the last one, right? So these are pairs. This is not pulling a number out and then pulling another number out, which is different from that first example that we did. Why we said 5 and 15 and 5 would be different. That's not the case here, right? So if we just count these up, there are how many ways? 5. There's 5 ways. Number 2 says telephone numbers in the U.S. have 10 digits. How many different combinations are there possible within each area code? So the first 3 numbers are my area code. And then there's 7 digits after that. So it's saying if all of this was the same, what would be the number after that? Okay? And notice that a local phone number cannot start with 0 or 1. So how many numbers do you have for your first blank? 8, then 10, then 10, then 10, then 10, then 10. So 8 and 1, 2, 3, 4, 5, 6 zeros, which would be 8 million different phone numbers within an area code.
I thought the area code was the first 3.
It is.
Why doesn't the 8 go there?
Because it's saying a local number, which means the first number after the area code. So local doesn't include the area code.
Wait, but you can't put, sorry, I'm just that number 1. You can't put some.
No, because I said distinct. We said distinct, yeah. Local is after the area code. This is the local number. Local means within that area code. Does that make sense?
Yeah.
Okay. I mean, if you think about it, have you ever met a 9541 something? Nope. Okay, can't do it. All right, number 3 says how many different ways can 5 couples pose for a prom picture? Assume each couple stays together. So there's couple 1, couple 2, couple 3, couple 4, couple 5. We don't have to worry about them as individual people. They have meshed together. They are now one. Okay, how many different ways can that be arranged? Is that permutation or combination? Does it matter the order? If I put 1 and 2 left and right and then I switch them, is that a new order? Yeah, so this is permutation. This is 5 factorial. 5 times 4 times 3 times 2 times 1, 20, 60, 120. Number 4 says find the number of distinguishable permutations for the letters weekend. Remember this, we take the total number of letters, 1, 2, 3, 4, 5, 6, 7. And then we put it over each repeated letter. So W only occurs once, but there is 1, 2, 3 E's. So it'd be 3 factorial, and then K's only once, N's only once, and D's only once. So this would be 7, 6, 5, 4, 3 factorial over 3 factorial. These cancel, and I get 42 times 20, 840. Questions on that one? Okay, 5 says you can answer only 12 questions from a total of 14 questions on an exam. How many different ways can you select these questions? It's not asking for how many different orders can those questions be put in, and that's the wording you got to be careful of, right? It's just saying if they were questions 1 through 14 and I only wanted to pick 12 of them, how many ways can I pick 12? And that is a combination. So this would be C 14, 12. 14 factorial over 14 minus 12 factorial times 12 factorial. 14, 2, 12. So I get 14, 13, 12 factorial over 12 factorial times 2 times 1. These are going to cancel. 2 goes into 14 7 times, and it's 13 times 7 or 91 different ways. So if it was like a permutation question, it might say something like there's 14 questions, and how many different order can you answer those questions? That's the difference between permutation and combination. Questions? Okay, this is number 4. It says in 2010, a certain state had 7 area codes using the information on the telephone. So I posted the example 4 with hopes to answer some of these questions. But it's basically telling you that there's, just like we did with the warm-up, there's really 2 parts to a phone number. The area code at the front and then the local part. Okay, this is saying there's 7 area codes. So the total of that is 7, not 777 or anything like that. There's 7 different area codes. Then it can't start with a 0 or 1, so it's 8, 0, 0, 0, 10, 10, 10, 10, 10, 10. So I would just multiply these 2 together, and I get 56 million different possibilities. So if it can't start with a 0 or the 1, that's why it's 8. Does that make sense? And then 10. Good morning, sir.
Hello.
All right, this says a school locker has a dial lock on which there's 32 numbers from 0 to 31. Find the total number of possible lock combinations when the lock requires a 3-digit sequence. So that's 3 digits, and each one has 32 in them. So I just do 32 times 32 times 32, which is 32,768. Okay, so this is 8-6 part 1. So we're doing probability part 1. So those of you that are taking any standardized tests this weekend, like it doesn't come at a better time. I'll tell you that much. Okay, because we're going to do part 1 today, part 2 tomorrow. All that probably will be fresh in your mind, and I can almost guarantee a probability question on a standardized test. All right, so the first thing is the probability of an event. Okay, we call any happening whose result is uncertain is called an experiment. So just some vocab here. The possible results of the experiment are called outcomes. The set of all possible outcomes of the experiment is the sample space of the experiment, and any collection of a sample space is an event. So the actual experiment could be like rolling the die or flipping a coin. The outcomes are heads or tails, okay? The sample space could be, if I'm going to do it twice, it would be a heads and a heads, and a heads and a tails, and a tails and a heads, and a tails and a tails, like that. That would be sample space. And then any sub-collection of a sample space is an event. So if you just wanted to talk about the first flip, something like that. When a 6-sided die is tossed, the sample space is represented by all the choices you can get, which would be 1 through 6. And then an outcome would be that you roll a 1, or you roll a 2, or you roll a 3, like that kind of thing, or you roll an even, or you roll an odd, that sort of thing. For the experiment to be fair, each of the outcomes is considered equally likely. So obviously, other than that, it's rigged. Okay, so we consider that to be a fair event. Example 1 just says find the sample space of each of the following. So 1 coin is tossed. What could be your outcome?
Heads or tails?
Heads or tails. 2 coins are tossed.
My Wi-Fi is like, I can't get.
So if 2 coins are tossed, what can you get from that? What's one possibility? Heads and heads. Oops. Heads and tails. Tails and tails. Tails and heads. Okay, there's 4 possibilities there. Oh my word. All right, the third is 3 coins are tossed. So what's one possibility? Heads, heads, heads. What's the opposite of that? Tails, tails, tails. What's next? Could you get heads, tail, heads? Could you get heads, tails, tails? You could get tails, heads, heads, tails, heads, tails. Do we do tails, tails, heads, and heads, heads, tails? So the way you know how many, if you've gotten them all, is if you think about it, these are 3 separate events, right? If it happens 3 times, how many ways can it happen the first time? 2. If it happens again, how many times can it happen then? How many ways can you get an outcome? Also 2. And it's a third time. Also 2. What's 2 times 2 times 2? 8. So go back to what you know about the number of ways, right? That should tell you that there are 8 options. Does that make sense? To see if you've got them all. Okay, so the probability of event occurring, if an event E has n E equal likely outcomes, so it's a number of outcomes, and its sample space has n equal likely outcomes, then the probability of event E is given by, this is so complicated, it's the number that you're trying to get over the total amount of sample space. So if I am flipping a coin twice, and I want to get heads both times, I'm going to say there's only one shot of that happening out of the 4 different outcomes. Does that make sense? Okay. So because the number of outcomes in an event must be less than or equal to the number of outcomes in an event, you can't have it happen more times than you're actually having that event. The probability will be a number from 0 to 1. So it could be a fraction, it could be a decimal, but it can't be less than 0 because you're saying there's absolutely a negative odds. That's not possible. That's not an equal, that's not a fair event. Okay? Or bigger than 1, saying that it's going to happen more than 100% of the time, and that can't happen either. If the probability is 0, it's impossible, and if it's bigger than 1, then it's, if it is 1, then it's a certain event. Okay? If I ask you if you're going to flip a coin, what's the probability you're going to get a heads or a tails, your answer is 100%, right? Because you're going to get a heads or a tails. Does that make sense? Okay, I will add this onto your assignment, but you need to know the deck of cards. But you need to know the deck of cards. First of all, there's 52 cards in a deck. First of all, there's 52 cards in a deck. One is hearts, there are 4 diamonds, one is clubs, hearts, one is diamonds, one is clubs, and one is spades. Hearts are red. Diamonds and hearts are red. Spades and clubs there are
aces, and then there's 2, 3, 4, 5, 6, 7, 8, 9, 10.
And then there's 2, 3, 4, 5, 6, 7, 8, 9, 10.
The ones that actually have faces on them.
The ones that
are
actually
called
have
face
faces
cards.
on them
Ace is not a face card because ace does not have a face on
Ace
it.
is not a face card because ace does not have a face on it. But you're going to get asked a lot of questions about a deck of cards, and I'm not going to give you a picture of a deck of cards. You got to know it, okay? So this one says a card is drawn at random from a standard deck of playing cards. What's the probability that it's an ace? So how many aces are in my standard deck of cards? 4. And how many total cards are there? 52. And that reduces to 1 over 13. So you'll leave it like that. Unless it says to give it as a decimal rounded, you will always leave it as your simplified fraction. Questions so far? Easy stuff, right? Okay, what happens when there's 2 events? There's something called mutually exclusive and not mutually exclusive. If 2 events from the same sample space are mutually exclusive, then they have no outcomes in common. For example, if you pull a card and it's a 5, you pull a card and it's a 6, you cannot have both a card that is both a 5 and a 6, right? That is mutually exclusive. Something like a 5 and a heart would not be mutually exclusive because a card can be both a 5 and a heart. Does that make sense? Okay, rolling a die and saying even or odd are mutually exclusive. Those are not the same thing. You can't get one that's both. However, even and under 3 would not be mutually exclusive because 2 would be even and also under 3, so it could happen both times. So the way you find it if it is mutually exclusive, meaning it can't be both, is you take the probability of the first event and you add it to the probability of the second event. So we are adding if it is a this and a this. So this says one card, and it's not and, sorry, or. One card is selected at random from a standard deck of 52 playing cards. What's the probability that the card is either an ace or a jack? And pay attention to the word or because eventually we're going to see the words and in here, and that's completely different. So what's the probability that it's an ace? We just did that, right? It's what? 1 over 13. What's the probability that it's a jack? Also same 1 over 13 because there's 4 jacks out of the 13 cards. Can a card be both an ace and a jack? No, so these are mutually exclusive, which means we simply just add them together. I'd get 2 over 13. So think about if I ask you, is it easier to get an ace or a jack? Or is it easier to get an ace and a jack? Or you basically are adding an option. Does that make sense? Yeah, so we increase our odds of getting it if I add an option. Down the road, we're going to add the word and end is harder, right? That means you have to pull both. That's multiplication, so we decrease our odds. So kind of keep those two separate things. Jacob. So you'd have to pull twice. Yeah, those are different. Yep. All right, not mutually exclusive events like we just talked about, ones that overlap. If they are not mutually exclusive, then you have to subtract the probability of the overlap from occurring. So you're going to find the probability of the first event occurring, the probability of the second event, and then you're going to subtract from it the probability of the overlap. So we're still adding here because it's an or, but this time the or can be happening in both, like at the same time. So we subtract off the probability of them both happening. All right, that looks like this. One card is selected at random from a standard deck of 52 playing cards. What's the probability that the card is either a heart or a face card? So can something be a heart and a face card? What would those cards be? A jack of hearts, a queen of hearts, a king of hearts. So there are 3 of these, right? How many would be just a heart? How many of the deck? 13 out of 52. How many would be just the face cards? So there's 4, right? There's 4 suits, 3 face cards in each one. How many face cards are there? There's 12. There's 3 here. I'll add them back in. Right? There's 3 face cards in each suit, and there's 4 suits. So there's 12 face cards out of the 52. You with me so far? So because this is mutually exclusive, we're going to do the probability that it's a heart plus the probability that it's a face card minus the probability that it is both a heart and a face card. So I'm going to say 13 over 52 plus 12 over 52 minus 3 over 52. Now I know you can reduce some of those, but you probably want to wait because now all the denominators are the same. So this would give me 25 minus 3, or 22 over 52, which becomes 11 over 26. Questions so far? Yep. That's if it's a heart and a face card. So there's 3, right? That would be both hearts and face cards. Yeah. Can it be both at the same time? So can a card be a heart and a face card? The answer is yes. That's not mutually exclusive, so you have to subtract at the end. If it didn't matter, if I said red or black, it can't be both, then it's mutually exclusive. All right, then we've got independent and dependent events. 2 events are independent when the occurrence of one has no effect on the other. For instance, rolling a die or a randomly generated number from a computer. These are things like with replacement and without replacement. So with replacement has no effect. Because we start with a fresh batch every time. Without replacement has an effect on it, and those are dependent events. So if they're independent, then I take this is an and statement. What's the probability of both events occurring? It would be the probability of the first event occurring times the probability of the second event occurring. So and is multiply, or is add. Good so far? Okay, a random number generated on a computer selects 3 integers from 1 to 20. What's the probability that all 3 numbers are less than or equal to 5? So I've got 1, 2, 3, 4, 5, 6, 7, all the way up to 20. Randomly generated, is that independent or dependent? It's independent. The first random generation has absolutely nothing to do with the second one, okay? So what's the probability that all 3 numbers are less than or equal to 5? So I want to know what's the probability the first number picked is less than or equal to 5, right? So I've got 1 first, second, third. So how many from 1 to 20 are less than or equal to 5? 5. So the first time, my chances of getting one that are less than or equal to 5 is 5 out of 20. You with me so far? Then it happens the second time, and it's an independent event, which means it starts with a fresh batch of numbers. What's the chances the second time? 5 out of 20. Then it happens a third time. It's also 5 out of 20. So these I would obviously simplify because it will make your life easier. This would be 1/4, 1/4, 1/4. And because it's an and, because we want all 3 to happen, we multiply these. Now that's an independent event. If you think about it, if I had said, you have 20 pieces of paper in a bag, you take out a number every time and you don't put it back. After you've taken it out the first time, now my numbers have gone to 19, right? The next one has gone to 18. And with those, which we'll talk about a little bit more tomorrow, you assume you get what you wanted. So it goes from 5 out of 20 to 4 out of 19 to 3 out of 18. Does that make sense? That's, God bless you, that's if it's dependent or without replacement, because they're the same things. We'll talk about that tomorrow. Questions on what we talked about today? Okay.